This section talks about homogeneous linear equations with constant coefficients. So I want to start with quick review of complex numbers because we need them here. The standard form for a complex number is a plus bi. That's the standard form of a complex number. A is called the real part, b the imaginary. This can be written in a trigonometric form called r cosine theta plus I sine theta, or some people use cis theta. And from this, Euler was able to prove a formula e to the I theta is cosine theta plus I sine theta. And the next thing is, if in general x plus iy a root for a function of x, then automatically its conjugate x minus iy is also a root for the same polynomial or function. So in this section, when it comes to go over examples, solving examples, it helps to know how to do factoring. So we have one of the factoring, x squared minus y squared. It's x minus y times x plus y. X cubed plus or minus y cubed is x plus y. X squared minus xy minus, well, let me do it this way, plus first, plus y squared, and x cubed minus y cubed, x minus y, x squared plus xy plus y squared. Good to know synthetic division. We might need that when solving or factoring polynomial functions. The quadratic formula, ax squared plus bx plus c equals 0. The quadratic formula says it's x equals negative b plus or minus the square root of b squared minus 4ac over 2a. The quantity under the radical sign, we call it discriminant. We call it discriminant. If the discriminant is bigger than 0, then the equation has two distinct real roots. If it's less than 0, it has two complex roots. If it's equal to 0, then you get one repeated root, namely x equals negative b over 2a. You can see why. Now to go back to differential equations, we learned this. We know that dy dx plus ay equals 0 has y equals c1e negative ax as solutions. You can check previous sections. We are interested here, we're interested to work with higher order differential equations. The first one was linear, y prime plus ay equals 0. So this is the same as y prime plus ay equals 0. We are going to look at higher order differential equations, starting with the second order. Ay w prime plus by prime plus cy equals 0. And then when we know how to do the second order, we can do higher order differential equations, like solve them. In the previous sections, we were given solutions where we're asked to verify them or try to guess another solution. But here we're actually gonna find the solutions, where they came from. So to work with this one, with the second order differential equations, what we do is, if you look at the linear one, the solution was c1e negative ax. That was the solution for that one. Now for this one, we don't know how to get this, but what we can do is, let's try to guess that y equals e to the mx, which takes the same form as you see on the upper right corner of the screen. E to the mx is a solution let's call this equation 1 for equation 1. Say that's a solution. Since I said it's a solution, it satisfies the equation, means I can find y prime, which is mx, and y double prime, which is m square emx, and substitute into 1. What do we get if we substitute? We get a m square emx plus b m emx plus c emx equals 0. Factor e to the mx out. That will leave a m squared plus b m plus c equals 0. So what does that tell us? We know that this term will never be 0 for all m and x. So this means if y equals e to the mx is a solution, then m must be a root of this equation, am squared plus bm plus c. Because this equation is 0, if the first term is not 0 or never can be 0, then what we get is this expression inside the parentheses must equal to 0. The expression inside the parentheses must equal to 0. And this expression that we got inside the parentheses has a specific name or special name. The am squared plus bm plus c equals 0, is called characteristic or auxiliary equation. This is called auxiliary equation. Now we're going to study equation 2. We study equation 2. How are we going to study that? That's a quadratic equation. And as I showed you earlier when I reviewed the quadratic formula, there can be three cases. Either two real distinct roots, or one repeated root, or two complex roots. Let's look at the first case. When equation 2 has two real distinct roots, namely m1 and m2. So what can we guess? Remember how we said y equals e to the mx is a root or a solution to the given differential equation. But you can say, wait, you're saying there are two real roots, m1 and m2, so there are two solutions, supposedly. Well, the way we do it, we call this y1 corresponds to m1, and y2 equals e to the m2x is the other solution. These are the solutions. Now the general solution, I'm going to call it y sub g, is going to be what? If you remember from previous sections, note the general solution comes from linearly independent solutions. And if these two solutions, y1 and y2, are these linearly independent? Well, how can we prove they are linearly independent? Does anyone know or remember? M is not zero. Check W. Wronskian. Yes, we can find or check Wronskian. So we need to find the Wronskian for this, and I'm gonna show it to you that this is not zero. The Wronskian for this, if you remember how to do it, you write this down. Then you find the derivative for the first one, derivative for the second one. And then find the determinant, this times this, m2e m1x m2x minus this times this, m1e m1x m2x. You can rewrite this as m1 plus m2 x m1e m1 plus m2x. We can factor e to the m1 plus m2x. That will leave m2 minus m1. Now, is this not zero? How do you prove this is not zero? Well, this one is never zero, no matter what m's and x are. And remember, m1 and m2 are the distinct roots. They are distinct roots. So this means m1 does not equal m2. Therefore, their difference is not zero. So this tells you this is not zero. So what does that tell us? This shows that the Wronskian is never zero. And hence y1 and y2 are linearly independent. Well, by doing so, this will allow me to write the general solution as c1e m1x plus c2e m2x. Where did that come from? It's a linear combination. It's the linear combination. Okay, we're gonna look at the next case. We looked at the case when M1 and M2 are distinct, where it has two real distinct roots. Now, one repeated root. And this means M1 and M2 are the same. So we can say y1 equals e to the mx. M or M1, whatever you like. So we can call this M. How do we find the second one? Can I take it as the same as e to the mx again? Well, we're gonna prove why you can or you can't, or if you can't, what is it gonna be? To do so, to find y2, you can use the reduction formula. If you remember, y1 integral e negative integral of p of x dx all over y1 squared dx, provided this is being used for this differential equation by prime plus cy equals to 0. And to solve for this, we need p of x, so we need to divide first by a, the entire differential equation. This is our p of x. We may substitute now. y2 equals y1 is e to the mx integral e negative integral b over a dx e to the mx square e to the 2mx dx. Keep this the same. Easy to integrate this because that's a constant x dx. Now, what am I going to do with this? How am I going to simplify this? Remember, when we did earlier, can I show you up here? When we did quadratic formula, we said that x, the root, is negative b over 2a for repeated roots. Negative b over 2a. So the root here, we can take m to equal negative b over 2a, multiply by 2 both sides. That tells me this quantity here is simply 2m. So y2 is e to the mx, e to the 2m, and there's an x, e to the 2mx dx. Watch how they simplify out. So I'm just integrating dx, and that would give us x e to the mx. That would be our second solution. So what do we get here? In summary, y1 is e to the mx, and y2 is x e to the mx. And keep in mind, those are linearly independent, and you can test it since the Wronskians is not 0. You can check that out if you like. Since they are linearly independent, the general solution in this case would be c1 e to the mx plus c2x e to the mx. Next case, last case. How about if the equation has two complex conjugate roots? So in the case of complex roots, how do we deal with this? We start by letting m1 equals alpha plus I beta. So because the two roots are m1 and m2 and they are complex, so each one can be written in a complex form like so. And since alpha plus I beta is a root, its conjugate, which is alpha minus I beta, is also a root. And this is similar to case 1. So similar to case 1 above. Or let me call it the first case. Remember how that was C1e to the m1x plus C2e to the m2x as a general solution. So here what we do, we just substitute. Instead of m, I'm going to put alpha plus I beta x plus C2 e to the alpha minus I beta x. Let's call this equation 3. One thing we have a problem with here is that we would like all the coefficients and the exponents to be real exponents and real coefficients. So we want real coefficients and real exponents. So we can't have like complex exponents when it comes to solving this kind of differential equations. Now, how can we rewrite this solution so there's no complex exponents? We start by using e to the I theta. It's cosine theta plus I sine theta. That's what Euler proved. And I'm going to replace theta with beta x. Why is that? Because if you multiply this out and this out, in the first one you're gonna get alpha x plus I beta x. So I replace theta with beta x. So that gives us ei beta x equals cosine beta x plus I sine beta x. Someone asking, what about e to the I pi? You don't need that here for now. So then we do the same thing for, if you remember this one, there's a negative I beta x. So negative beta x for theta. E negative I beta x equals cosine beta x. If you put negative beta x, sine negative alpha is negative sine alpha, so it's minus I sine beta x. With these two substitutions, that gave me two equations, which I'm going to add first. That gives me ei beta x plus e negative I beta x equals, the imaginary parts are gone. We get 2 cosine beta x if you substitute this back into the first equation, or you can multiply the second equation by negative and add, or you can say subtract them. That will give us e to the I beta x minus e negative I beta x. That gives 2i sine beta x. So now we look back at equation 3. In equation 3, for simplicity for now, in 3, I'm going to let C1 equals C2 equals 1 for Y1. And same thing for Y2. So what do we get if you write that down? So Y1 is E alpha plus beta I, no more C's, X plus E alpha minus beta I, X. What you can do with this, rewrite it alpha X times E beta I X plus E alpha X times E negative beta I X. We can factor e to the alpha x out. That will leave e to the beta I x plus e negative beta I x. Notice something. Look on the top of this page, this screen. What do you see? E to the I beta x plus e to the negative I beta x is 2 cosine beta x. So what I got? I can replace this with 2 cosine beta x, which you can take the 2 out, e alpha x cosine beta x. What happened? What happened in Y1? No more complex stuff. No more i's. Right? Isn't that magic? Oops. That's for Y1. We can do the same thing, same for Y2, e to the alpha plus beta I x minus e alpha minus beta I x. That's Y2, the conjugate of Y1. What we can do, rewrite it alpha x times e I beta x minus e alpha x times e negative I beta x. We can take e alpha x out. That will leave e I beta x minus e negative I beta x. What is this quantity, e I beta x minus? Look, on the top of this screen, we proved it's 2i sine beta x. 2i sine beta x. Take the 2i out, e alpha x sine beta x. That's Y2. So I found Y1 and Y2. Then the general solution is CY1 plus CY2. It's a linear combination. C1. Y1 we proved it's 2e. So that 2 is the constant, which you don't need. It's within C1. Alpha x cosine beta x plus C2, that's as a constant that takes also the 2i goes in there within C2, and that'll leave e alpha x sine beta x. And this can be rewritten by factoring E alpha x out, and that will leave cosine C1 cosine beta x plus C2 sine beta x. So let's apply everything we learned to some specific examples. Solve number 1, y double prime minus 3y prime plus 2y equals to 0. To solve such a differential equation, that's a second order differential equation. First thing, we find what we call the auxiliary or the characteristic equation. The characteristic equation is the y double prime, so y prime is like an m. Y double prime is m squared. Some people use lambda. So here you get m squared minus 3m plus 2 equals to 0. And you might say, wait, what happened? Where did that come from? Okay, let me scroll back up and show you exactly why this works this way. We proved why it works, but I'm going to show you again. So if we go to all the way up, notice equation 1. It's similar to the one I'm just trying to solve, right? A y double prime plus b y prime plus c y equals 0. When we did the work on this, we got to this part. Do you see it? It was a y double prime. So the y double prime became m squared. The y prime became m, and the y is gone. Do you see that? So the differential equation can be rewritten as a quadratic equation like this, which we call the characteristic equation. So if there's like y triple prime, then you put m cubed. Y to the 4th power, you put m to the 4th. Now it becomes like a simple quadratic equation. You can use quadratic formula, or if you can factor right away, as I'm doing, that will save time. So m would be either 2 or 1. Notice, what did I get? These are two real distinct roots. So that tells me case 1. Case 1, the general solution for case 1 was C1 E m1x plus C2 E m2x. Y general, C1 E to the 2x, C2 E to the 1x. That's the solution. Now, how do we check that you got the right answer? What do we do? Well, you find y prime for this and y double prime, and then substitute them back into the original equation, the one that is written in blue, and then that will show to you that you will get 0 on both sides. So let's see what we can do. The characteristic equation, I'm going to use lambda, okay, just for fun. Lambda squared plus 1 equals 0. How do you solve this? Well, lambda squared is negative 1. Lambda is plus or minus the square root of negative 1, which is plus or minus I. Or you can write it 0 plus or minus I. So alpha here is 0, beta is 1. The general solution, if you remember, it was E alpha x times C1 cosine beta x plus C2 cosine beta x. Oops. Cosine then sine. So y general is E0x C1 cosine x plus C2 sine x. e to the 0 is 1. You can leave it like this if you like, or you can get rid of e to the 0. Next example, try this one. The auxiliary equation is m squared minus 12m plus 36 equals to 0. So m minus 6 times m minus 6. So as you can see, m1 is 6 and m2 is 6. It's one repeated root. And to finish solving this, what we do is we use the solution for the third case, which says c1e to the first one plus c2, don't forget the x, e to the 6x. How about something like this, subject to or provided the conditions y of 0 is 4 and y prime of 0 is negative 1. So the auxiliary equation is m squared minus 8m plus 17 equals to 0. And this one is not easy to factor by trial and error. We can use the quadratic formula. 4 times 17, 68 over 2a. Negative 4 under the radical becomes 2i. So this is like alpha and beta is 1. So the general solution is e to the alpha x c1 cosine beta x plus c2 sine beta x. But it's not done because they give us some conditions. They give us y of 0 is 4. So let's substitute x0 and set this equal to 4. E to the 0, 1. So it's c1 equals 4. And let's find y prime from the general solution. Using product rule, 4e to the 4x times c1 cosine x plus c2 sine x plus e to the 4x negative c1 sine x plus c2 cosine x. They give us y prime at 0 is negative 1. We can apply to this equation 4e to the 0 c1 cosine 0 plus c2 sine 0 e to the 0 negative c1 sine 0 plus c2 cosine 0 equals negative 1. So that's a 4 cosine, this is gone, sine 0 is 0. So c1 plus, this is 1 here, c2 equals negative 1. But c1 we found at 4, so that becomes 16 plus c2 negative 1. So c2 is negative 17. We can go back to the general solution that we found earlier and substitute c1 4. So it's 4 cosine x minus 17 sine x. That's what we need. You asked, how about for order, higher order? If it's like order 3, what happens? For higher, for higher order differential equations, with order n, say in general, so for nth order differential equations, the y general, which is, let's look at the first case when we have distinct real roots. Okay, then you get C1e m1x plus C2e m2x for the first case. That's when we had two distinct real roots. If we have three distinct real roots, then it goes up C3e m3x. How about if we have n of them, because the order is n, then it goes all the way to Cn e mnx. That would be the solution. So it's kind of like the extension of the first case. How about the complex? Actually, for the second case, not the complex. Second case, the y general for nth order differential equation, it would be C1e m1x plus C2x e m1x, because it's a repeated root. Then C3x squared e m1x all the way to, let's call it ck e x k minus 1 e m1x. And I'll show you an example what happened in the third case. For the meantime, so now what we have, look at an example. Solve y triple prime plus 7y double prime plus 15y plus 9 equals to 0. Again, we write the auxiliary equation or the characteristic equation like so. Oops, wait. There is... wait. So y triple prime plus 7y double prime plus 15y prime plus 9y equals to 0. So the characteristic equation is m cubed plus 7m squared plus 15m plus 9 equals to 0. How do we factor this or solve it? If you remember from algebra, you can do grouping, but grouping is not going to work out here. The other way to do it is use something, a theorem. What is it? What do we use? Rational root theorem. Yes, rational root theorem. The rational root theorem said you take all the factors of 9, plus or minus 1, plus or minus 3, plus or minus 9. And the number in the front is 1. That makes life easier. If it's not 1, if it's, let's say, 2 or 3, you need to list down the factors of that number and then do division with the last ones with the first one. So if you try 1, notice something, all the coefficients are positive. So you don't have to worry about all of them, just worry about the negative ones, because the positive one will not make it 0. So one of those negative ones hopefully is going to work out. You can check it by substituting that in, or you can do synthetic division. 1, 7, 15, 9. Negative 1 goes here, bring that down, multiply this by this, add, multiply this by this, add, multiply this by this, add. Oh, it worked. So as long as the remainder is 0, it's working. So that tells me m equals -1 is a root. So m plus 1 is a factor by the factor theorem. And what is left from the synthetic division? Do you see these numbers? 1, 6, and 9. 1m squared plus 6m plus 9 equals to 0. And what do we do next? m plus 1. This is m plus 3 times m plus 3. So m1 is -1. m2 is the same as m3, the same as -3. So the solution would be y equals, for the first one, c1e negative x plus c2e to the -3x plus c3xe negative 3x. Do you see why? Because it's repeated, so we do x here, we put an x there. If it's not repeated, we don't put x. So this would be the solution. The next example, solve y triple prime minus 27y equals to 0. So to solve this one, we start with the auxiliary equation m cubed minus 27 equal to 0. This looks like m cubed minus 3 cubed, which we gave you a formula for it to review today. Factor this out, m minus 3, m squared plus 3m plus 9. See, factoring is important for this section. So what do we get? M equals 3, or m squared plus 3m plus 9 equals 0. We need quadratic formula for this. Negative b plus or minus the square root of b squared minus 4ac over 2a. Negative 3 plus or minus negative 27, which is 3i squared of 3 all over 2, which I like to write as negative 3 halves plus or minus 3 halves I squared of 3. Then the general solution would be c1 e to the 3x for the first one, plus here we have the complex conjugate e alpha x. Alpha is negative 3 halves. This is alpha, this is beta, times, I already used C2, so C1, I'm gonna use C2, cosine beta x plus C3 sine beta x. Is that okay, guys?